Hello, everyone. I can't believe we're making it right before I stop being president, but we are now recording IITT episode number 32. So we almost covered all the technical committees. And today with us, we have TC204 with amazing speakers covering underground construction and tunneling. And I would like to start by introducing our speakers from all around the world. I'm going to share my screen. Uh, so, with us today, we have Professor Anna Wan-Huan Zhou from the University of Macau, representing TC204. And she's going to tell us a bit about the TC activities and talk about settlement prediction for shield tunneling. Our then expert Francesco Petrella. I love innovation happens when academia and practice develop, overlap. Francesco is in Arup, Denmark, director of Arup Ground Engineering. Thank you for being with us. Amanda, our young engineer lecturer from the University of Technology in Australia. She's going to talk about digitalization platform for model tunnel construction. I can't wait to hear all of you. And please interact. I'm sure the audience are going to be fascinated, but we're going to say this is very important in geotechnical engineering. And I'm so excited. I'm going to start by giving the floor to Anna. The floor is yours, please.
Thank
You
you.
can share your screen. I will stop sharing mine.
Here's showing all right. Okay, thank you, Mark. And then good morning, everyone. So I'm Hannah, and then according to the schedule, at the very beginning, I give some idea of our TC. TC204 was established in 1989. So it was first chaired by Professor Kenichi Fujita, and then another 2 terms under Professor Robert Mayer, and then Richard Custer with 1 term, and then the last president, vice chair is Professor Adam Benjuaji. And then now currently the chair is Professor Julia Vigiani in Cambridge University. So our TC is underground construction in soft soil. And then we mainly focus on the geotechnical aspects of underground construction, especially the deep excavations, tunnelings, and the major underground structures. Particularly, we are focusing on the analysis, modeling, and the monitoring of the ground movements and the interaction with the existing structures and the mitigation measures, risk management aspects. Our terms of references are being updated in the website. You may look into more details. It includes the dissemination, guidelines, recommendation, conference assistance, and the industrial links. I would say we are very active at TC. Currently, the executive group, including Julia and me and Andrew Franza, and then we currently have a weekly regular meeting to discuss the issues in our TC and activities. So we have our membership 69 over 29 countries. And we are also trying to encourage more participants, involvement of young researcher practitioners, and as well as the represented people from South Africa and even the South America. So one of the important activity in our TC is the International Symposium Underground Construction in Soft Ground. It was first started in New Delhi in 1994, then it continues organized in around the 2 years of cycle. But the last two, one in Cambridge was a little difficult because it was originally designed in 2000, but because of the pandemic, that was delayed to 2022. And even with a good number of submissions and proceedings, but we don't have many people to participate in person. And then the last one was successfully held in Macau 2024. And because I was the chair of that conference, I would like to share a little bit more information here. That was a big event of our TC we held in Macau 2024. And this is the opening. And we have about 160 participants from over 15 countries, because it's near to the Asia, it's in the Asia, near to mainland China. So in that conference, we have much more participants from mainland China. And on the right side, you also see Albert Zhou that showing coming to the conference to showing the support from the ISSMGE. And then during that conference, Adam presented the first Fujita lecture, and then we have other keynote speakers. So, and then that conference will also make a poster session, which attract a lot of interaction during 2 days of conference. Although we have a very tight schedule, but always people are walking around during the coffee break and then the session. So the roundtable session is also very special. Last time, then we have invited all of the keynote and those people on the stage and the local industry people on the stage. And then we have a discussion, like 40 minutes, on the topic of underground construction in historical areas and tunneling across sea and coastal zones. Because these two topics are both are very important for the future underground development of Macau. So we have a good insights from all the experts. So this is a proceeding from the TC, from that conference, and the site visit and the banquet. You are seeing these pictures of the traditional Chinese dragon dance. And our TC also support international conference related events, like the coming Vienna conference. We have session, especially our TC has lead a joint workshop with TC204, TC222, TC309. And that workshop will include representative contribution from each TC and also a roundtable discussion and also one keynote. And then the next host of IS conference is a little bit, again, complicated because of the Middle East situation. The decision in 2 years ago has to be cancelled. So Doha actually originally designed, but now we consider not possible to continue. And in March, we just called for the candidates. And luckily, within a very short period, we received 2 candidates, touring and also coming forward. And then with their passion and the local support, they just presented their presentation in our plenary meeting last Friday. Yes. And then our TC member will vote. Yes.
We have to go faster for the TC.
Yes. Okay. Then that's a linking page for our TC. And also we have an instant message.
I will follow.
Yes, thank you. And then more important is also related to the topic I'm going to share is that we are having a task force, including me, Jamie, Andrea, focusing on the case history and the database, because we consider this is important aspects in all the project construction and management. It's different from the case research paper and with database because there are some data and then not really recorded related to published paper could be very useful in the future research. So we consider this should be recognized and be well documented. And my topic today will be, sorry?
I like to tell you and the audience that we're just launching now a new journal for ISSMGE for research. So we have a journal for case studies, and we have now a new journal for research. Both aspects, like you were showing, are, I hope everybody will be excited to publish with our journal, the
Yes,
international
yes,
journal.
that's right. We just nominated our member to the journal for the editorial board. Yes, yes.
Go ahead.
And
Thank you.
yes. Yeah, the topic today focusing on settlement prediction for the shield tunneling, but actually I will just focus, introduce some of the previous and ongoing work here related to the tunneling settlement. And of one idea I would like to highlight is that underground construction is a complicated and systematic problem with a high uncertainty. And the uncertainty comes from uncertain geological conditions, which everyone acknowledge. And then, but still, we are having problem even in recent years. And then, of course, the other activities and the data are not really well recorded, and then human error, etc. And so the topic today will involve some of three projects. One is the metro extension line in Hangzhou, and the other two as large diameter shield tunnels. So the Hangzhou project is regarded as a twin tunnel case. It's a very interesting twin tunnel case. Yeah, so this is a project of the twin tunnels. One first line on this side, and then the second line on the side. So first line going ahead, and second line followed. So it's very long. It's more than 1,000 meters. So along the construction, they have well documented settlement distribution of the tunnel. So we try to analyze, and then that with also the diameter, the spacing of the twin tunnel is changing along this line. So we could observe, okay, the twin tunnel caused the surface settlement pattern changing with the different d over d. D is the spacing. D is the big D is the tunnel diameter. And then this with 264 maximum surface settlement observations. So just jump to the results. You can see that the figure on the left, it is the smallest D ratio, 2.84. So a little bit more than 2 times of the spacing. That will be the diameter, 6 point something for the tunnel diameter. So the blue line is the surface profile, transverse surface settlement profile when the first excavation tunnel passing. And then the red line is the additional settlement caused by the second tunnel excavation. So the first plus the second additional is the last, the black line. So that is showing a W shape. So this one is well recorded, and then it is changing with different D ratio. And we actually can see when the D over 4 times, over 4, then this pattern dismisses. All right. So the first line, first tunnel has this very symmetric distribution. The second also symmetric distribution. So this actually is well documented, and then we have observed this pattern, and then analyzed the pattern. And in addition, because during the construction, we also have a lot of geological condition. For example, the soil type may change, and the soil overburden height change, cover depth changing, water level not change too much. And we also have a lot of shear operational parameters, so that we analyze this using other data machine methods to make a data feature selection and even prediction. I would like to go to details. I think the data is the most important part. With the well-documented data and labeled data, our newly techniques can do a lot more. And then another about the large diameter shear tunneling. One completed work is about the Greenhart Canal in Netherlands. It's regarded as the biggest one in 2004 with a diameter of 14.87. And then this tunnel is going through a sandy soil with
I can see the little
semi-qualified.
person at the bottom,
Little person? Oh,
14.9
yes.
here.
You're
Yeah.
right, because it's really big. Yes, with
Yeah.
the peat and clay overlying. So this is there is a concern about the excess water pressure during the tunneling. And then in that case, it's a very rare case that the contractor has installed a number of poor pressure transducers around the tunnel, around even at the places very near and far away, and ground pressure transducers, slurry pressure transducer. Okay, then there have been 1,600 time steps of recording. On the left, you can see the water pressure is increasing and dropping during the drill and the standstill procedure. So we made this analysis. Just use the genetic programming method that can simulate the different this pressure distribution. But this is purely data-driven approach. Because of the data, we could do this easily, and then we can plot this spatial temporal excess water pressure distribution when the tunnel is processing. So, but of course, because it uses all the data, so it performs much better than the one-dimensional conventional transient model, which can only utilize limited data. So that is another topic. The last case I would like to present is the ongoing project in Macau. This will be the largest and even it's still ongoing slurry pressure shield tunneling. So it is underground and crossing the sea from the E zone to A zone. Both are artificial island. So make a connection between the two islands. And then one, I would like to emphasize the case means it's multi-source data. The multi-source data include geological data that include around 25-meter intervals boreholes, 402 boreholes, and then of course means additional soil parameter, geological knowledge have been done before and after the drilling. And then we have the TBM. Now the machine is very advanced, so a lot of operational data can be transferred in real time. Thrust, torque, advance rate, grounding pressure, those are automatic. But there are also very important engineering logs. For each ring drilled, there will be 250,000 data points, along with the engineer's assessment of the ongoing operational condition of that ring and the resulting action. So these logs we are also trying to collect and how they change the pressure in the front and the grounding pressure, and sometimes they even change grounding materials to control the post-settlement. So in addition, because we have a collaboration of the construction company, when the tunnel before the tunnel going into the sea, there's a sea wall. We are very concerned about, because the limited distance, we are concerned about the deformation caused by the tunneling, the large diameter. So we have installed additionally this in-depth settlement and the water pressure, and then deformation, lateral, vertical deformation monitoring at a different distance. So these are very comprehensive monitoring results. And this, of course, this tunnel went through very well, but I think this data recorded will be very valuable for future research, because this tunnel is just not perpendicular into the sea, crossing the sea wall. It has an angle. Okay, so with this small radius angle and then also large gradient, descending gradient, it's about 0.5%. And then because of this small radius, the tunnel is always turning. So the pressure on left and right has always a little bit different. And our soil response on the two sides also different. And in addition, with the data, we are ongoing doing the analysis about the control tunnel settlements uplifting by the property and pressure volume of the grouting materials. And then we are evaluating and prediction of the sandstone condition using the data monitored by the accelerometers installed in the chamber. Yeah, because of limit. And also this work is ongoing, so I hope that I have other chance to present our results in the other occasions. Okay, that is all. And my final conclusion is that the underground construction is uncomplicated and a systematic problem with the high uncertainty. Field monitoring is very important, and multi-source data is valuable, and they are underutilized the future studies because most of us, the current studies focus on the data of one project. If we can utilize the more data from multiple projects, that will give us much more insights. And then there's a problem of mismatching of different projects. And machine learning is very powerful in prediction and given sufficient and standardized data, label, and knowledge. Thank you. Thank you. That's all my presentation. I hope didn't over time too much. Thank you.
Can I say something?
Yeah, please.
I'm really happy and impressed by your presentation. I learned so much. Really nice. This field monitoring and ongoing value engineering basically is so important, and you stressed on that.
Yes.
I want to thank you so much. You are the expert.
I believe we have much more to do. Yes.
You did so.
Thank you.
Yes, you said it, and hopefully we'll meet
I'll
again.
stop my sharing.
Yeah. Francesco,
Hi. Thanks for the
floor is yours.
yeah, thank you. Thanks for the introduction earlier, and thanks, Hannah, for your presentation. I too was impressed. It's also good to have that overview on the TC204 activities. I've joined the
Amazing.
TO4. Can you see my screen? Yeah, I joined the TO4
Yes.
quite recently, back in October. I'm Italian, but I live in Denmark. Been living in Denmark for a while, and I've had the pleasure of collaborating as a practitioner, collaborating with academia over the years. So today,
I see. You make me happy to see practitioners
yes,
part of the ISSMGE family. I'm probably the only president coming from practice
yeah,
in the
that's
history.
unusual, isn't it, Mark? Yes. Yeah.
So
No,
keep
that's really
going,
good. So, I mean, in underground construction, we're always trying to link what we observe in projects to how we design, right? So the whole idea around this presentation is how do we get observation become design knowledge? So there will be just a few words about why case history still matter in our industry, and how academia and practice can work together to turn data into insight. And then there's a couple of case histories that I will borrow from the A project here in Copenhagen, just as an excuse to make a few points. And then I'll touch on the advancement that satellite monitoring, as opposed to terrestrial monitoring, can offer to the industry. And then a few words on how all of this ties into EC7, which in this part of the world is Eurocode 7 widely used. And as you know, we're at the second generation now coming. So I would start from a quote which is almost 50 years old now, that the benefits that derive from well-documented case histories are undeniable. That was Berland who said that. And the reason is simple. And as Hannah was saying, there's variability in the ground. The ground is variable, is uncertain, is only partially known. Every design relies on models, therefore, and all models are a simplification of reality. And then on top of that, many of the effects we care about or we need to worry about are induced during construction. So effectively, reliability cannot just come from calculations. It has to also come from observation, measurements, and just learning from past projects. That's why case histories are still important. And really, case histories are how our discipline actually builds new knowledge. So, coming from projects to novel projects to knowledge, I want to take one example, which I consider the Copenhagen Metro as a living laboratory. There's been very many metro lines, and I use this to make a few points. There's been more than 10 years of collaborations between the metro company, 2 Danish universities, and also other universities, also in Italy now contributing, as well as the company I work for, Arup, and others. So it's really to follow that continuous loop, or you could say virtuous circle of monitoring, analysis, publishing the work, and then going to an improved design. And this takes years. And we started many years ago with just master thesis and asking some enthusiastic students to start back analyzing the behavior of many of the stations that have been built in the city, or also the many kilometers of tunnels. Then it became PhDs, and with lots of technical papers at the beginning, conference, and now also journal papers. So as a result, already now there's really a significantly improved understanding of ground movements in Copenhagen. So this is the first of 3 case histories. I'll be brief. I'll stay within the 15 minutes. The first one is about parameter correlation, and it's just a snip of one of the stations that has been built, and it's a deep excavation in this case, right? And traditionally, we treat geotechnical parameters as independent variables, but and then we work with single best estimate, and obviously there's different terminology depending on where you work in the world, right? Characteristic parameters, etc., etc. But actually, this case study shows, and the analysis we've done, that ground parameters are correlated, and actually ignoring these correlations distorts prediction. And I should say that this that I'm presenting here has just been published on Geotechnique, and it's the work mostly of Efthymios Panagiotis, who's the PhD student who's now is a doctor in philosophy. So he's finished his PhD at DTU, which is the Danish Technical University in Copenhagen. So instead of identifying one set of parameters, we updated full parameter distributions, and we compared 2 cases. One in doing the back analysis, one where parameters are treated as independent, and one where correlations were explicitly included. In the next slide, you'll see input parameters that we used. I don't expect you to read every X and Y axis, but if you look at scenario A and B, effectively scenario is the correlated data set, and scenario B is independent. So it's the gray and the blue. And on with that basis, and using monitoring and a probabilistic back analysis, we concluded, or we could observe, that we had better predictions with the correlated data set. So for example, if you look at the top figure, where scenario A, like I said, is the independent and the B, the correlated, you'll see that there's actually, for an excavation stage, the first excavation stage, and then followed by the anchor installation, there is a superior reproduction of the behavior with correlated parameters. If we go on with the excavation, the x-axis changes a bit. Here too, scenario B for the intermediate excavation stage 2, and the final excavation stage, we have a superior back analysis. So the outcome is that, first of all, there's better prediction, but also importantly, we can obtain a faster and a more stable back analysis, almost by one order of magnitude, because it took us 8 times fewer analysis when we worked with correlated data sets.
Francesco,
yeah.
Can you zoom on the graphs? Just explain the snake. What is the gray zone is zoom on the 4 graphs.
I'll try.
Because I can't see.
Is that better?
Yes. Scenario A, B.
That's zoomed in. So in the left-hand side, there's the same excavation stage. That's just the first.
So as you go deeper.
Yeah. As you go deeper, there's more displacement. I was warning you that there's a different x-axis. That's unfortunate. But to say, as you go deeper, this is the second excavation stage. This is a multi-propped, you could say, excavation. It's supported by anchors.
Your x is the settlement?
Horizontal displacement. Horizontal displacement of the wall,
okay.
yeah. And this is the depth. So the bounds are the prediction range, and then there's the comparison between what has been measured in black and what has been back analyzed, and the difference between scenario A and B is whether you use independent parameters or correlated parameters. As you can see, there's a better sort of back analysis with correlated parameters.
Thank you. It's clear. I'm playing the role of a viewer.
So. That's very helpful. Thank you. The next one is for the M3 line, which actually preceded this one, and it focuses more on settlement that occur behind the wall. Again, another deep station box, in this case supported by secant pile walls with multi levels of struts. You can see that here in plan, and there's a building alongside it. Hence the interest, of course, in the settlement caused by the horizontal displacement. And here you can see.
Was it done top-down technique?
We've called it hybrid, in that the slab went in first, and then the rest of the construction proceeded bottom up. So only the slab went first, and then you went down with the props. And then as you built your slab, permanent base slab, permanent intermediate slab, you remove the props. So it's like a hybrid.
The slabs, okay.
And this is because the stations for M3 were all in the urban area. And so there was a wish to lock in the wall at the head to limit displacement. Stiff glacial deposits, that's typical overlying limestone. It's typical of the ground conditions here. And then basically, we were comparing prediction approaches that are typically used in the industry and here. Empirical design curves or analytical ground loss methods, and obviously the benchmark being the measured settlement behind the walls and the wall deflection themselves. And the results are quite clear, and I'll take you through them. Basically, the empirical design methods tend to overestimate the settlements, typically by a factor of 2 or 3. And they also overestimate the extent of the influence zone. Whereas in contrast, the measured behavior shows smaller settlements and a more localized response. So if I zoom in, I'll do that again. On this right-hand side, on the left, you see the wall displacements. These are the horizontal displacements for 2 inclinometers that are opposite each other. And then with the solid circles, those are the measurements. So very limited settlements, less than 5 mil. And then with the dash or the continuous curves on this in the central part, so figure B and C, you will see the predictions in greenfield conditions or in the conditions where you have a building next to the wall. And then with the on the right-hand side, you see the back analysis that was done, which shows a better alignment with measured data. Basically, when we switch to a ground loss approach, which links the settlements to the actual wall deflections, the predictions improve significantly, and particularly when based on monitoring data or calibrated against previous projects. So the key takeaway is that rather than relying on generic envelopes that are on textbooks, we should always use observed behavior to inform and calibrate our predictions. And this work was published at last year's WTC in Stockholm. I'll finish with a few words about satellites and the insert technology. Another tool, you could say, these days we have in our toolbox, so that we don't solely rely on terrestrial monitoring, but we also have satellite monitoring. The real power of this technology is the archive, is this data set, is the ability also of going back in time. And we can build, and that allows to build a baseline even before construction starts, which helps us to identify assets, critical assets that may already be undergoing settlements before any project or works begin. And instead of having a handful of points scattered around, we get a district level view. On the right-hand side, you see that's a zoom out of Copenhagen, which helps us see patterns and not just isolated readings. It's helpful before construction, like I said, for baselines and focusing the terrestrial instruments where the risk has highest. It helps during construction to fill in the gaps. And it's helpful, of course, after construction to have long-term monitoring and screening of anomalies. And on the right-hand side, there's a case studies we have looked at, where these are the dashed line at the alignment of 2 of the tunnels. And then we've looked at certain terrestrial monitoring equipment, and we have plotted displacement, so settlement, over time. And with the triangles here, that's the terrestrial monitoring data, whereas these green and purple bands are the satellite monitoring, which align quite well. But as you can see, they help you go back in time and demonstrate, the client was able to demonstrate, therefore, that there was ongoing settlement of certain assets, and it wasn't the passage of the TBMs that were causing the settlements. There were other factors at play. These days also.
This is a great observation. I love satellite monitoring.
Yes, and
there are new satellites being launched now with different wavelength. You can see through vegetation.
Yes.
We will be able to see.
Through vegetation.
Because I'm using it for a project in a jungle, a highway crossing in swamp areas. Thank you for mentioning it.
Of course. Last slide. Bring it all back to the beginning in a way, and why experience is so important. And observing also that the second generation of Eurocode 7, there is a subtle, let's say, but important shift. The code makes it clear that we need to compare our results with previous experience now, and that design must be supported by monitoring, inspection, and reporting. It also required construction records, geotechnical construction records to be prepared to capture what happened. And if you look at the part 2 of EC7, it goes even further. It explicitly promotes back analysis of monitoring data to derive best estimate parameters. So what used to be good practice is now becoming embedded really on how we design. So we're moving from a mindset where case histories are something we publish to one where they're part of how we verify and improve our work. And in other words, they're not just sort of an academic output, they're becoming part of quality assurance and continuous improvement. And as a final reflection, I would say that if we're not systematically capturing and back analyzing our projects, we're not fully complying with the spirit of modern geotechnical design, and we're certainly not learning as a profession. Thank you.
Thank you, Francesco. You presented the second generation of the observational method.
Thank you.
My favorite keynote lecture is marriage between theory and practice.
Yeah.
Amanda, I hope you're ready.
Yeah, I'm ready. I'm going to share my screen.
Oh, it's yours. Yeah. Francesco, if you can stop sharing, please.
Yeah.
Yes.
Thank you.
Can you see my screen? Yeah.
Looks
Yes.
good.
Okay. Right. Thank you. Thanks, Marc, for that introduction, and thanks, Hannah and Francesco, for the beautiful presentations. I definitely seeing a lot of synergy from your presentation to things that I'm going to share. But I'm probably going to switch the flavor from construction stage to the design stage a little bit, or the planning stage. So I'm going to talk about some of the work that we did as an endeavor to integrate some digital tools into one single platform for modeling tunnel construction. One of my favorite diagrams to show, these are some of the recently completed tunnel projects in Melbourne, Australia, and also the ongoing projects at the moment. So the two tunnels sitting in the center, the Melbourne Metro Tunnel Project and the Westgate Tunnel Project, are recently completed and open for public use last December. And the long loop kind of thing surrounding the entire Melbourne is the Suburban Rail Loop project. That is a very exciting and significant state project with a projected life up to 2056 in Melbourne. It's currently ongoing. The Eastern package is currently ongoing. They're doing site establishment and early ground clearance works. And then the Cyan one is the North East Link project. Again, another road tunnel are going to link the eastern part of Melbourne to the northern part of Melbourne. So all of those are very exciting for anyone who's working in the tunnel industry, working as a geotech engineer, and also researchers in that domain. However, as Hannah rightly pointed out, everyone sitting on this call knows that tunneling and underground construction isn't risk-free. We're actually quite risk-prone, and especially a lot of those risks and hazards remain uncertain, especially in the earlier planning and designing stage, and that uncertainties continue into the construction stage. And the main issues are related with ground movement and also some geotechnical uncertainties as well. And as the practitioner or researcher in this domain, we are trying to leverage existing tools to understand or to streamline the pipelines of techniques to help us mitigate that uncertainties as early as possible. And a good framework that probably you also know is what we refer to as DICWE framework. data, information, knowledge, and wisdom. So we start with data collection, the traditional geo investigation methods, borehole loggings, to the remote sensing that Francesco mentioned as well, to geophysical prospecting techniques, and even nowadays we may send little robotics to do some imaging inside of the like a prior hole or like a pioneering holes. And then once we gather those raw data, we perform some analysis and trying to extract useful information through digitalization methods and visualization methods. For example, the building information techniques is currently quite popular, and the traditional geological modeling techniques is also a good way to visualize those data. And we also process them through more AI-driven methods, machine learning, deep learning, computer vision as well. After those, we can then perform simulations and analysis to understand what are the potential consequences and how can we propose mitigation measures to maybe do some ground improvement and change the support configurations to again improve the success rate of the project. And apart from geotechnical considerations, we may also consider other factors or key players on the table to holistically enhance that decision. So this framework is quite powerful and can be actually applied to many different projects throughout the entire project life cycles. So we also, as part of the team, we also did some, let me move back to that slide, work for tunnel design and considering carbon emission as a key factor and trying to do multi-objective optimization to, I'm not sure what's going on with that slide, to improve the tunnel safety while not compromising its sustainable performance. Okay, it really wanted me to move on. That's fine. And another way to look at that framework is what we call a multi-level digital twin. So depending on with the increasing level of complexity of information gathered from a static way of representing the existing asset or the to-be built asset, we can actually incorporate some dynamic updates by incorporating more sensing and more inspection and more monitoring, as both of our other two speakers mentioned about data, which is really, really important. We can then start to answer questions from what is it to why it is happening or what is happening, to then through the simulation and evaluation to predict what will happen in the future. And finally, in an ideal world, that the digital twin can also prescribe the mitigation measures, saying, oh, in this situation, you can actually do this. So the workflow we've been taking for design and construction is mainly object-based modeling, which is a beam-oriented object database. And then in the, I'll say, a multi-platform collaboration stage, we actually allow models created by different platforms to be integrated and federated in order for us to understand their interaction. And finally, once we actually have real-life project data, we can then do back analysis to validate our simulation and our numerical model. So the increasing level of details, as I sort of touched on in the last slide, we actually can construct a model at different level of details. That includes the geometrical details as well as the semantic details, and for them to serve for different use cases. For example, the very low level detail 100, we can probably use it for spatial clearance checking, and then the level of detail of 300 is a good detail level for numerical simulation for geotechnical analysis. And finally, the level of detail of 500, which includes all the fit outs, all the detailed elements, is probably more suitable for construction management scenarios like quantity takeoff and detailed cost estimation. So just have a quick look of how can we do that parametric solid modeling. So this is a demo that's showing we can actually instantiate the solid model by actually prescribing the number of segments, the internal radius, and segment thickness, and also segment widths, and select the alignment, any alignment that you created. That can actually pop up like a linear model. And also we can increase the level of detail by now setting up the actual segment configuration and then created a segmental line tunnel model. Oops, next. And once we have our asset models being set up, of course, we then move on to the ground modeling or geological modeling stage. There are, again, many different types of platforms facilitating these purposes. So in this case, it's a commercial software, but we can also duplicate this same process in a BIM environment. Oops, we can stop this. So we can also instantiate all the boho instances and then create a ground model in a again commercial BIM platform. So all of them are actually featured with its geotechnical properties, as well as obviously its the strata geological forms. And similarly, we can also establish a building model in the same environment by pulling out the information of the building height, the shape of the building, and geo-reference them again in the same platform. So once we have all of those disciplinary model, we can integrate them together so they form this federated model for analysis. And there are many different ways to do.
And sorry to interrupt, what software are you using for the digital twin of the tunnel?
So in this example, I'm using Revit, which is a software from Autodesk. Yeah, it's a BIM platform. So it's quite recognized and probably used by industry as well. And then we have many ways to perform analysis, no matter it's empirical and analytical or numerical model. And the easiest to do is to actually embed the analytical model into our federated modeling environment. As a quick, probably during preliminary design stage, this serves as a quick way to check stability of the tunneling activity. So we embedded two analytical solutions. The first one is the volume loss, the Gaussian formation, and estimate the settlement trough. And the second analytical solution we embedded is convergence confinement method. The three significant curves, the ground reaction curve, the support characteristic curve, and of course the longitudinal deformation profile. And all of them, because they are essentially associated with the ground characteristics or the ground properties, and also the tunneling methods, all of those information will actually be embedded into the modeling platform. So we actually input the alignment. This is actually the alignment from the suburban rail loop Eastern package, and also the ground model of all the existing buildings. And we then prescribe the ring depths, the tunnel radius, the list of tunneling methods, and we can actually select tunneling methods. And whoops, I think I accidentally clicked on something. Sorry, let me move back. And we can then visualize the final impact of tunneling on the ground surface.
Hopefully it's minimal.
It is not too bad. It is not too bad. And yeah, we're using this color coding to actually differentiate from significant settlement to minimal settlement, and also identify buildings that are prone to those ground volume loss. And similarly, we can also perform this by ring, because we actually allow each single ring to intersect with the actual geological component. So if they're traversing two strata, actually the ground loss will be different. So we can also look at the individual ring performance as well. Oops, that's interesting. I'm not sure why I'm not showing that. Maybe it's this one. Yeah, sorry, it's this one. So we can actually see the settlement at each single ring as well. And similarly, we can do the longitudinal deformation profile for seeing the convergence of the actual segmental line tunnel. So similarly, we embed all of those analytical solutions into the model to allow us to visualize the excavation as tunnel excavates the deformation surrounding that structure. So we actually, we set up, we try to make this platform as user-friendly as possible. So we use some terms that practitioners may appreciate, hopefully. So what I've just shown is meaningful analytical solutions, but we definitely can do exactly the same thing with numerical, with like more advanced numerical models. Basically, we used BIM as the foundation to establish all these geotechnical properties and attach them with the model. And then we convert the model along with their properties into the numerical model, purely driven by script. And then we can actually visualize the post-analysis effect back in the BIM environment. It's simply because many times the BIM model is controlled by the digital engineering team, and the actual numerical modeling or simulations are performed by geotechnical engineers or tunnel engineers that do not often speak the same language. So this hopefully can bridge these two workforce together. And we can also actually perform this for other type of tunnels, like hydraulic tunnel in this case. So we can actually simulate the crack. Again, we can model out, actually instantiate the crack instance in a tunnel segment, and then perform numerical simulations for that. So in this example, we actually did for hydraulic tunnel, and then we changed the configuration of that tunnel, and we can actually simulate if there is any defects existing in that asset, what will be the impact and what will be the remaining service life of that asset. So similar philosophy and similar mechanisms being applied. And finally, bring back to this slide, I think both myself, Hannah, and Francesco have mentioned there are a lot of more advanced ways to simulate and to predict our tunneling and underground construction. We've definitely seen the wave of AIs impacting all of us, but they're still tools, and we should select the tools and use them wisely to make our work more efficient and to benefit more projects. So finally, acknowledgement, thanks to all my collaborators and also industry collaborators for support and some references for everything I've reported. Thank you very much.
Amanda, amazing, beautiful presentation. Thank you, all of you, for, complimenting each other. I'm
Yes.
complimenting you because
Yes.
you really deserve it.
Yeah, I also, I'm very interested this
Amanda, if you stop
nice
sharing.
presentation from
Yeah,
Francesco
I'm trying to
and
stop.
Amanda.
Yeah.
Yes, and also
Yeah,
this
yes,
working digital twin, and also it's it's really amazing. But I also can see a lot of work ahead. You mentioned the numerical model that can be, because the analytical model certainly cannot represent the three-dimensional complicated situation. Yes, and Francisco also the working the deep excavation and the publications. So really congratulations and very nice presentation. Thank you.
Thanks so much.
I hope to see you all very soon in Vienna.
Definitely.
I probably will see you next week, another ITT. Mark?
Oh, you're gonna be
Yes. Okay.
okay. In
Yeah.
Vienna,
Thanks so
I will
much.
say goodbye.
Yeah.
And now I say
Yeah.
goodbye for the IITT in Vienna as president. So thank you and have a great week ahead.
Thank
And
you.
we'll
Thank
stay in
you.
touch as one family.
Thank you.
Thanks all.
Thank you.
Ciao, ciao.
Bye-bye.
Bye.